Now we move on to the third session, 3D additive manufacturing. A historical speaker at the JTF, Dr. Ulrich Klotz, who speak about additive manufacturing of platinum alloys. He got a degree in engineering on physical metallurgy at Stuttgart in Germany, and a PhD in material science at HT Zurich in Switzerland. He is the director of the Department of Physical Metallurgy at the Research Institute on Precious Metals and Metal Chemistry FEM in Germany, in Schwagingen. The production of additive manufacturing of platinum alloys is at the center of increasing interest. On the one hand, because platinum implies challenges on traditional technology, and then because it's good to do 3D laser printing. The study analyzes the effects of the interaction between laser and platinum alloys at 9050 with different alloys. You have the floor.
Thank you.
Thank you very much. So thank you very much for this kind introduction. I'm very happy to be here and meet some of my friends and colleagues after these 2 years. And it's my pleasure to present you some results about the additive manufacturing of platinum alloys. We heard already about the possible alloys that are available for platinum, and also some general remarks about additive manufacturing in the talk of Chris Corti. And so this helps me to continue with that topic. I want to show some practical aspects during the laser powder bed fusion melting of jewelry items. So I will start with a short motivation, show our experimental procedure, our results, and summarize my talk. So I mentioned laser powder bed fusion technology. We've heard about selective laser melting. Some people speak of laser beam melting. These are different names for the same technology. The principle is that you have apply a powder bed in a machine. The powder bed has a layer thickness of 20 to 50 microns, sometimes for steels even higher. And this powder bed is melted at some positions with a laser, and so the part is melted layer by layer because the platform is lowered each layer. So this has some benefits and drawbacks compared to investment casting techniques. We have shorter process cycles. We can produce parts faster. There is a reduced amount of precious metal required because we don't need to cast a tree and a sprue. Fewer consumables are needed, and we get comparable roughness and porosity as previous studies showed. But of course, there are also some drawbacks. So this is a very simplistic comparison. We have much higher machine costs, higher costs for metal powders and supplies. And well, the last point is actually not really a drawback. We need alternative design for such parts, but actually this is also a benefit of these 3D printing technologies, that we can realize alternative designs by 3D printing or LPBF process. So what did we do in our study? We wanted to know about the effect of the alloying composition. And to study this, we used sheet material. So we prepared small metal sheets that we put into our machine, and we applied laser tracks on these machines. because this is much easier than producing a powder. Producing a powder means a very large effort. You need a relatively large amount of metal to melt, and therefore we went this way by using this laser track on sheet material. Then we used a commercially available alloy by C. Hafner to do some laser powder bed fusion experiments. We did a small parameter optimization, and I will show you an example about how the support structures are influencing the result that you obtain. And we did a small optimization of such support structures. And of course, we did the characterization by microstructure and porosity, and manufactured some jewelry items as examples. So this is our approach on using the laser tracks. This picture shows you platinum alloy sheet with different laser tracks. We use different compositions, binary and ternary alloys, and several 950 platinum ruthenium based alloys. And you see the laser tracks have different thickness, which is depending on the laser speed. All tests were done at the same laser power. So the smaller the speed, the wider the laser track, because the more energy per time unit is applied onto the material. So we measured the width of these laser tracks, and also did cross sections to measure the depth of the laser tracks. Well, of course, the way how the material reacts depends on its physical properties, and these are the melting range. Usually the lower melting, and the wider the melting range, the wider the depth is, and the wider and deeper the laser track is. The same is true if the reflectivity is influenced, or if the thermal and electrical conductivity is influenced by the alloying elements. Now here's an example how the laser width, line width of this laser track depends on the laser speed. So we see with what we see already on the picture, that with increasing laser speed, the laser width is decreasing, and the process gets more stable, because the scattering of so this is the maximum and minimum values. It's shown by the color range. The scattering is reduced, and here we see a cross section. So you see the sheet material, the deformed sheet material, and here you see the cross section of the laser track. So we measured these values, and we see an effect of the laser material interaction. There are two principal modes that are distributed, which is the conduction mode and the keyhole mode. I will show you an example how this looks exactly here. So here we see a very small laser track with low depth. You see the scale is 40 microns. So this is a typical example for the conduction mode. This is done in a 600 platinum alloy with palladium and copper. And if the copper and palladium ratio is exchanged, so here we have 300 palladium, 100 copper, and here we have 100 palladium and 300 copper. So the copper-rich alloy shows a much deeper laser track. This is a typical example of the keyhole mode. So here the scale is even higher, so this laser track is really much deeper. And if we plot the width and the depth, so the blue points are the depth, which are determined from the metallographic section, and the orange points are the width. We see the width is more or less constant, but the depth is increasing, and there is a maximum at around 20 to 30% copper in this platinum, copper, palladium alloys. So we see that the alloy composition has a strong effect on the depth of these laser tracks, and this is important because we have to melt layers together, so we have to assure that each layer is melted perfectly to the layer below. But on the other hand, if the energy input is too high, we can get porosity inside the material during the keyhole effect. Now here are some other examples. We used several ternary alloys. These are based on 950 platinum ruthenium. And in this first graph, I show some examples with high melting additions. So we used copper, cobalt, gold, and replaced some of the ruthenium. So on the left side, there is the platinum ruthenium alloy. And on the right side, there is the platinum copper, the platinum cobalt, platinum gold alloy. And we see that, if you look at the triangles, the depth is not affected by copper, but we see an increased depth if we add some cobalt or gold to this alloy. So we have not fully understood what is the reason, the physical reason for that, but I think it's an effect on the solidus and liquidus temperature that results in a certain melting range by adding these alloys. So I think these are interesting results when it comes to a fine optimization of the alloy composition for such applications. Now, if we use some low melting alloy conditions like gallium, indium, tin, germanium, or zinc, we get very different effects. So here we used a series of 950 platinum alloys. They contain 20 copper and 10 ruthenium, and then the copper was replaced by other alloying elements, or additions were made. Additions were made of other alloying elements, and we see that the width and the depth are influenced by some. So here's the platinum ruthenium copper alloy, and we see indium, zinc have little effect. We also see this here. There's very little effect. But other alloying elements like tin, germanium, or gallium, they have a very strong effect. We get this keyhole mode if we add germanium. In the case of gallium, we also get the keyhole mode, and we get a lot of cracks. So there are some critical alloying elements. So we heard about the H-hardenable alloys in the presentation of Chris Corti that contain gallium. So I suppose that they might be critical in the processing with the laser powder bed fusion or SLM process, because we have they lead to so-called segregation. So certain elements are concentrating in the liquid phase and strongly reduce the liquidus temperature. So this means we have a liquid phase remains and results in cracking during if the cooling is continued. However, indium and zinc show no effect, so that's was a bit surprising for us, but that was the observation that we also confirmed when we worked with alloyed powder. So in the second step of the study, we used alloyed powder. I already mentioned it's a commercial alloy powder, platinum gold indium alloy by C. Hafner in Germany. And from this alloy, we built little test parts. So these are a wedge type sample with some wires of different thickness. And with a small plate with different angles. So we want to simulate some structural features of jewelry objects. And there we did a parameter variation. you see that depending on the parameters, you can get very different results in terms of porosity. We determined the porosity by looking at this blue area marked here, and we measured the porosity by optical metallography. And this is a plot of the porosity as a function of laser parameters. We've changed the laser speed as a function and measure the porosity, and we also changed the so-called hedge distance. The hedge distance is the distance between two laser tracks. The laser is going forth and back to scan an area, and the distance is called hedge distance. And we see that the hedge distance has actually a quite strong effect on the porosity, especially at higher laser speeds. We see that with decreasing hedge distance, the porosity increases. And this is probably due to an overheating, because more material is melted several times. While an increasing laser energy is also increasing the porosity, and this is increasing laser speed, and increasing laser speed is also increasing porosity, because if the speed is too high, the energy is missing. Anyway, we found very low porosity values. So this is 0.2% of porosity, which means 99.8% density. And it's easy to obtain values below 1%, which would be here. So we can obtain values of 99% density, which is more than comparable to cast platinum objects. We heard also in Chris Corti's presentation. And it's also, the porosity is much lower compared to 18-karat gold, where we have, with our machine, under comparable conditions, we achieved porosity levels of 1 to 2%. So now we built some ring samples, some typical jewelry samples for stone setting. We used this type of support structures. So here you can see our small test piece. And if you look carefully, you see that something is wrong here at the right side of the ring, but only on the right side. So if you look in detail, we see that the surface is porous here, and some material is missing. And of course, this is a non-acceptable defect. And we looked at the surface. We made a build job and interrupted here at the critical height, and then looked at the surface of the ring shank. So this is shown here in these pictures. So here the left ring shank looks very good. The surface is perfectly lasered. There is no roughness, very low roughness. While on the right side we see so-called balling. So we get little droplets of melt. We get a large porosity. If we look at the cross-section in the metallography, we see very large pores. And this is a clear indication of overheating. And we were wondering why this is the case, because both sides were processed with the same parameters. And at the surface, we also see later a certain roughness. So if you look here at the surface, we see a very porous, spongy surface. It looks like some material was there as a vapor and condensated on the surface. And we also see some hot cracks, which can occur as an effect of overheating. This is the condensate in detail, how it looks. And this is an elemental map, so it shows the distribution of platinum, gold, and indium. So all elements are present in this condensate. It's clear that it's coming from the alloy, and especially the indium, which has a very low melting point, is concentrated. So this again confirms the overheating of this area. So why is this happening? This is our 3D model of the ring with the structures, and on the right side we see a sketch. We applied the powder from the left with a wiper, and we also start lasering from the left, and then we see if on the left side when we start lasering, due to the geometry, there is solid material below, so the energy can be dissipated into the ring shank, while on the right side, in the very beginning of the laser process, there is a powder bed below this region. So the energy cannot be dissipated, and therefore we get this overheating. And the solution is to optimize the heat dissipations by applying suitable support structures. To do this, we analyze the ring geometry. Usually, a rule of thumb is all areas that have an inclination of lower than 45% need support. So this would actually only be this area. But we found from the analysis that on the left side we have about 60% that need supports, and on the right side more than 70 degrees angle needs supports to avoid this superheating. So we need much more supports than just supporting 45-degree angle. And if we analyze the CAD file and which are the regions that show angles of 60 or 72%, we mark them all in red, and we see that we need more supports on the right side compared to the left side. So we applied such supports, and this was the original parameter with the defect here. Then we used the new supports. You can see them here, and this could fully avoid the problem of the overheating on this side of the ring. Now let me summarize my presentation. Such laser track experiments are good to easily evaluate the effect of alloying elements, because you can easily prepare them and not much material and effort is needed. We see that some elements are critical. Gallium, tin, germanium, they increase the melting depth. They are critical in terms of hot cracking. And then in terms of the alloyed powder that we used, we found that we can achieve very low porosity levels over a wide range of process parameters. However, it appears important to do a proper heat management of the part, so it requires a careful analysis which regions need support structures, and this is especially important if you have many different parts that you want to produce. So there are rules of thumb, but it's better to test them if they are working for your particular part. So with this, I want to thank you. I want to acknowledge my colleagues that contributed, also the funding from the German government, and I thank you for your interest.